Hey guys, welcome back. We're still talking triple integrals. Now we're shifting gears and going to spherical coordinates. The first thing that I want to just acknowledge really quickly is the fact that whenever you are converting to spherical coordinates, you need to add rho squared sine of phi. This is incredibly similar to when we start looking at cylindrical coordinates, and we always add that extra r whenever we're integrating. One of the cool things is that the next lesson that we're going to do is Jacobian. And when we do the Jacobian, you are actually going to see where these are coming from. So this is actually not random. It actually makes sense. And so when we do Jacobian in the next lesson, I'm actually going to prove to you guys where the R comes from when we talk about cylindrical coordinates, but just a friendly reminder that when you're doing these problems, you will always add a rho squared sine phi to every single integral. All right. The other thing that I will tell you guys is that when we're doing spherical coordinates, usually the questions are written so nicely for us that it's not too terrible for us to actually set up our bounds. So these are actually a little bit easier in my opinion because of the way that they're written for us. So let's get into this question. It says, let's use spherical coordinates to evaluate the triple integral of b of x squared plus y squared plus z squared of dv, where b is a unit ball, and that unit ball is x squared plus y squared plus z squared is less than or equal to 1. So the first thing we're going to do here is we're going to look at rho. And so remember that x squared plus y squared plus z squared is actually equal to rho squared. Again, it's written for us because it's right here for us too. So rho squared is less than or equal to 1. So remember that since rho is a distance, right, from the center out, very similar to how the radius is for cylindrical coordinates. Technically, it would be the -1, but since it's a distance, rho is going to be between 0 and 1. So that's going to be the bounds for our rho. And then since we're looking at a unit ball, right, so a unit ball, very similar to a cylinder or sphere, so a little ball that we have here, then the other two that we're going to look at for bounce wise is going to be our traditional bounce for that. So what I mean by that is that for theta is going to be all the way from 0 to 2 pi, right? There is, it's a ball around. So we just go 0 to 2 pi for this problem. And then phi is going to be our traditional from 0 to pi. And remember that just because we haven't done it in a while, that phi is going to be the angle from the positive z-axis outward. And so the furthest out it can go is up to pi. So these are going to be the bounds that we're going to use when we set up our problem. So it does not matter which one of these goes first. So I'm going to, because I'm just going to randomly choose. So I'm going to go ahead and do phi first. So 0 to pi, I'll do theta second, and then I'll do rho third. Rho is usually the first one that we always do here with this problem. So those are going to be our bounds. Remembering that we do need to change x squared plus y squared plus z squared into spherical coordinates. So that's just rho squared. We've actually already talked about that here. And then we're going to add, so I'm going to change the color up. We're going to add another rho squared sine phi. So please, guys, remember to do that. All right, always add this to every spherical coordinate system. And then we're going to do our change of rho, change of theta, change of phi. Okay, so as I said before, just setting up everything is actually the majority of our points. Right, this is really what I care the most about. So what I'm going to do now is I'm going to pause the video and I'm going to write out the solution to this because I try to keep these videos as short as I possibly can. So just do some simple integration and then we'll come back, talk about that. We'll move on to the next problem. All right, so I'll pause it. I encourage you guys again to pause it as well, solve the problem and see what you get. All right, guys, so here's our solution. The first thing that I did here is actually do our rho squared times rho squared is rho to the 4. Then when we started integrating with respect to rho, remembering that sine of phi is an actual constant. So we just leave that kind of alone. And so do 1/5 rho to the 5th, evaluate from 0 to 1. And so I pulled the 1/5 out. And then when we integrate with respect to theta, again, sine phi is completely a constant. So that's why we just add our theta here. And we evaluate it from 0 to 2 pi. So again, I put the 2 pi in there, and then brought it out. And then we get down to a very simple problem where we're just integrating sine phi from 0 to pi. So that becomes negative cosine of phi. I pull the negative out, and then I evaluate the cosine of pi as -1, minus the cosine of phi is 1, and then I get the answer of 4 pi over 5. So, like I said before, guys, a couple things just to say as we're leaving this problem. They are going to write these problems for you that are pretty easy and standard. But the last thing that I just want to say to you guys is that whenever you are converting to spherical coordinates, you will always do a rho squared sine phi in that interval. All right, as you see right here. So that's where we're going to finish this video. I'll see you guys in the next one. Take care.